Now today we will talk about velocity and acceleration in 2 dimensions and 3 dimensions. So we've been talking about velocity and acceleration concepts only in 1 dimension, and now we're going to extend it and figure out how things are going to work. So what is the central problem of classical mechanics? Well, the central problem of classical mechanics was the fact that if we have x, which is a position of any object, as a function of time, can we predict what that object is going to do at a future date? This is the equation that we get for a one-dimensional motion. Now that we have the object in 3 dimensions, we can generalize the same expression, because the central problem of classical mechanics will not change in 2 or 3 dimensions, and we can generalize it to, instead of having in x, we can call it an r. R as a function of time. Mathematically, this equation is read as r as a function of time, where in 3-dimensional motion, the vector r is going to be represented as xi plus yj plus zk. So what do we have to do in order to study motion in 2 or 3 dimensions? In order to study motion in 2 dimensions or 3 dimensions, we need help from our friends, the vectors. Positions, velocity, acceleration in 2D and 3D are determined not only by specifying their magnitude, but also their direction, again in 2 dimensions and 3 dimensions. So what's the difference between going from 1 dimension to 2 dimension in different things? Well, here's what it is in a nutshell. So the position in 1 dimension is described as x, whereas in 3 dimensions it is defined as a position vector r, which has the vector x in it, but it's just a part of a bigger picture. Displacement is defined as delta x, whereas in 2 dimensions the displacement is defined as a displacement vector. Velocity is displacement per unit time, and in 3 dimensions velocity vectors is the change in position vector per unit time. The sign is equals to, the sign in both cases is the direction of the displacement vector. Acceleration is a change in velocity per unit time. Sign is equal to the sign of the velocity difference. Acceleration in 3 dimensions is exactly the same thing. Change in velocity vector per unit time, and the direction is equal to the direction of velocity difference of vector delta v. So I don't know if you've noticed, but they're exactly the same things, except now instead of talking about x, we are talking about r. So the velocity in 2 dimensions and 3 dimensions. The definition of the average velocity, instantaneous velocity, that applied to the motion in a straight line will now also apply to the motion in 2D and 3D, as long as you add and subtract them as vectors. So the average velocity definition now becomes change in r, which is a displacement vector, over the change in time. The instantaneous velocity will now become delta r over delta t in the limit when delta t becomes very, very small. So let's look at what we're actually talking about. So suppose we have a particle that is moving along the blue path as shown here. At time t1, its position is ri, and at time t2, it has moved and its final position is rf. Now in this case, instantaneous velocities are given by the black arrows here, vi and vf, and these are tangent to the path that is being followed. For average velocity, we will now have to find delta r, which is a change in position from ri to rf, and this is going to tell us what the average velocity of these 2 points is going to be. And note that this points in the direction of delta r. Since v is a vector, velocity is a vector, we are going to use a displacement that is also a vector quantity.